let's talk a bit about algorithms. You may have seen division of algorithms into following groups: some sorting algorithms, searching, recursion, divide and conquer, backtracking, two pointers, and so on. It's important to keep in mind that these groups are not totally different. For example, merge sort is an example of divide and conquer and could be recursive at the same time. Also, merge sort, quicksort, binary search are concrete examples of algorithms, while recursion, divide and conquer, backtracking are whole group of algorithms. So first, the algorithm could be either iterative or recursive. We have recursive approach here, but the iterative approach is almost never mentioned in systematizations like this one, but it's very important. For example, as a beginner, you the most probably have faced with iterative algorithms only. Let's briefly explain both approaches. If we have some array of 5 elements, and our task is to calculate their sum. First, we can use some for loop to iterate through the whole array and add first element to the sum, then add the second element to the sum, move next, next, and so on, and add the last one as well. Here we have 5 iterations, and that's an example of iterative approach. That's some kind of most intuitive way for doing this. But there is also a recursive approach. For the same input, we want to find the total sum as well. In terms of recursion, we can achieve that by adding first element to the sum and call the same function again, but for some smaller input. We are not considering the whole array anymore. We are just considering the rest of elements. So here we have new array and apply the same approach. We add the second element to the sum and do the same for the rest of elements. Then add number 3 to the sum and call the same function for 4 and 5. Add 4 to the sum and call the same function for 5. And we have 5 and we don't have any elements remaining. So we add element 5 and we stop with the recursion. It's important to have the exit condition to know when to stop the recursion. Except division of algorithms into iterative and recursive, we can divide them considering which operations we can apply to different data structures. When we have some simple data structures, like numbers, we can add them, subtract, divide them, and so on. When we have some arrays, lists, and so on, we can also apply different operations. For example, add, remove, get element, search for some element in the array, or sort the whole array. So let's take a look at some simple examples. If we have array 1, 2, 5, 4, and 3, and we want to add element 6, our original array will be turned into this one with 6 added at the end, for example. If we want to remove element 5, our original array will be turned into this one without element 5. If we want, for example, to get some concrete element, let's see, second one, this is first and this is second, we will get element 2. If we want to search for some element to check, for example, if there is element 7 in our array, we will get the false. And if we want to sort the array, our array will be turned into the sorted one. Also, there are some operations for some more complex purposes that are used so often that they have their own name, like two pointers and sliding window. We will discuss later these approaches in detail on some concrete tasks, but the first one is applied for the optimized traversal of arrays, and sliding window is useful when we are dealing with some subarrays. So we covered two pointers as well. Merge sort and quicksort are famous examples of sorting algorithms, and binary search is a well-known example of searching algorithm. But we still have some algorithms that are not yet classified, like divide and conquer and backtracking. Based on design approach, we have the following algorithms: divide and conquer, backtracking, dynamic programming, brute force, and greedy algorithms. Let's take a look and briefly explain each approach. For divide and conquer, uh, if someone imagines a number from 1 to, for example, 100, let's say 37, and we want to guess the target number in as few attempts as possible. One possible solution will be to start from the beginning and check if that the target is element 1, 2, and so on, up to 37. Also, we can start from the end and check in this direction. But we will have, starting from the beginning, 37 iterations, and starting from the end, 64. But let's see if we can do it better. Instead of starting from the beginning and checking each element, we can start from the middle of array. We check if element in the middle is target. So if we have numbers from 1 to 100, the middle is 50. And we check if the element in the middle, 50, is target. If no, like here, we ask if our middle is smaller or bigger than the target. Here, the middle element is bigger than the target, so we need to look further inside the left part, from 1 to the middle, 50. So now we are not considering elements from 1 to 100 anymore. We know that our target is in this range. And we apply the same approach. The middle is now 25, and we check if middle, which is now 25, is target. No, it's smaller than target, so we need to look further in the right part. In the next step, we are considering the range from 25 to 50. The middle is 37. We found the target in only 1, 2, 3 steps in this case. Also, it's important to be aware that sometimes it's better to start from the beginning. For example, if the target is element 2, or it's better to start from the end, linear, if the target is 99. But in the most cases, this approach will do the best job and we will find the target the faster. This concrete searching example is called binary search. This whole approach is divide and conquer algorithm, and the core principle is to focus on smaller parts while solving the main big problem. So here we had 100 elements. Here, in the second iteration, we have only 50 elements, and here we have only 25, and so on. If the target didn't 37 but some other element, we will take a look at, for example, 13, 6, and so on. But we will have less than 10 iterations even in the worst case. Backtracking approach is related to the following logic. We are starting from some point until the some place where we don't know how to move on. We will choose one option, for example, left, and if it turns it was the wrong choice, we will come back and choose another option. Such approach is called backtracking. Now let's take a look at dynamic programming. Imagine we want to track working hours during 1 month. We want to know at the end of each day how many hours we have from the beginning of month. So for example, on first day we had 8 hours, then 6, 10, and so on, 7, 9, and 10 hours. First day is easy because we know that we had 8 hours without any calculations. Then at the end of second day we have 8 plus 6, 14 hours in total. For the third day we can apply the same. We can say 8 plus 6 plus 10, but there is no need to do that because we have this part already calculated and we can use the previously calculated result and just add today's hours to it. And we have 24 hours at the end of the third day. Then let's say that here after the 28th day we have 210 hours. Here we just add 9 to it and we have 219, and here we just add 10 to it and we have 229 hours. So the dynamic programming is based on memorizing previously calculated results and use them instead of doing the calculation each time from scratch, which will result in doing a lot of unnecessary and duplicated calculations. Let's take a look at brute force and greedy algorithms. So, brute force is often the worst algorithm came on your mind. Of course, sometimes it has to be applied due to nature of task, but in most cases there is some better and more optimized solution to choose. Let's take a look at a simple example. We have an array 1, 10, 15, 2, and 3. And our task is to find the biggest element in it. Brute force approach will look like following. We start from the first element, 1, and iterate through all other elements to check if our element is maximum or there is some element that is greater than it. So we want to check if our element is greater than all others in the array. And here we know that 1 is not greater than 10, so 1 is not maximum. Then for 10, do the same. Iterate through all other elements and check whether 10 is greater than them. 10 is greater than 1, but 10 is not greater than 15. So 10 is not the maximum. For 15, we do the same. Since 15 is greater than all other elements, we found the maximum. Also, we could have at the end some large number, for example, 200, and in that case, 15 wouldn't be our maximum, and we will need to iterate through the whole array and end with 200. So here we have some kind of double set of iterations. First, to iterate through all elements, and then inner iteration for each element to iterate through all other elements, and so each time. So we have double set of iterations. And it's not so efficient. But there is no need to apply double set of iterations. With greedy algorithm, we want to act greedy, to choose the best option we can at the moment. So let's take a look at the same example. We are starting from the element 1, and since we are greedy, we say it's our maximum for now, because we don't have anything better now. Then we move on to the next element, 10. 10 is greater than our current maximum, so we are overriding it and update our maximum to 10. 15 is greater than 10, so we are setting our maximum to 15. 2 is smaller than 15, so our maximum says 15. And 3 is smaller than 15 as well, so our maximum is 15. And here we have only one set of iterations. With this, we covered the core concepts of algorithms. There is one more important topic related to algorithms, their time and space complexity. We will briefly explain it in the next video, and then we will be ready to start solving LeetCode tasks.